Hi everyone, welcome to Chapter 13, Bioenergetics and Biochemical Reaction Types. This chapter is mostly a review of chemical concepts that you have already studied. What we are going to do in this chapter is use those concepts and apply them to biochemical systems. So, let us discuss more on this. These are the learning goals for this chapter. Application of thermodynamics to biochemistry. Common organic chemistry principles in biochemistry. We'll learn about high-energy biomolecules, their hydrolysis and group transfer reactions. And finally, redox cofactors such as NAD+ and FAD, which serve as universal electron carriers. Metabolism is the sum of all chemical transformation taking place in a cell or organism. And it occurs through a series of enzyme-catalyzed reactions that constitute metabolic pathways. And the small molecules that happen to take part in these metabolic pathways are termed as metabolites. And metabolism is a process that involves two different steps: anabolism and catabolism. While catabolism is the degradative phase of metabolism in which organic nutrients are converted into smaller, simpler end products such as lactic acid, carbon dioxide, and ammonia. Catabolic pathways release energy, some of which is conserved in the form of adenosine triphosphate, NADH, NADPH, and FADH2. The rest is lost as heat. Anabolism, on the other hand, which is also called as biosynthesis, happens to convert these precursor molecules into larger macromolecules, and in the process uses these energy that are stored in ATP, NADH, NADPH, and FADH2. And so, the big picture from the slide is that energy relationships happen between both anabolism and catabolism. And these energy carriers that are shown here are used in anabolic pathways, which are actually made in catabolic pathways. The laws of thermodynamics can also be applied to living organisms. Living organisms cannot create energy from nothing. That is not going to happen. Living organisms cannot destroy energy into nothing. Living organisms may transform energy from one form to another. In the process of transforming energy, living organisms must increase the entropy of the universe. In order to maintain organization within themselves, living systems must be able to extract usable energy from their surroundings and release energy that is not used back to their surroundings. Let us review our knowledge of free energy and equilibrium. In order to drive chemical reactions, cells need sources of free energy. Free energy can be gained from non-equilibrium systems moving toward equilibrium. Free energy is governed by the equilibrium constant, K equilibrium. For the equilibrium reaction, AA plus BB giving CC plus DD, where small a, small b, small c, and small d are the number of molecules of big A, big B, big C, and big D. K equilibrium is given by this equation, and the standard free energy change is given by minus RT ln, the product of the concentration of C to the power C times concentration of D to the power D divided by concentration of A to the power A times concentration of B to the power B. The standard free energy change of a chemical reaction is thus simply an alternative mathematical way of expressing its equilibrium constant. This table shows the relationship between standard free energy change and the equilibrium constant. If the equilibrium constant for a given chemical reaction is 1, the standard free energy change of that reaction is 0, as you can see. If the equilibrium constant of a reaction is greater than 1, for example, 10 to the 3, the standard free energy change is negative. If the equilibrium constant is less than 1, for example, 10 to the minus 4, delta G, or the standard free energy change, is positive. Because the relationship between equilibrium constant and free energy change is exponential, relatively small changes in standard free energy corresponds to large changes in the equilibrium constant. Free energy, or the equilibrium constant, determines the spontaneity of processes. When K equilibrium is greater than 1, delta G is negative, and the reaction proceeds forward. When equilibrium constant is 1, delta G is 0, and the reaction is at equilibrium. When the equilibrium constant is less than 1, delta G is positive and proceeds in the reverse direction. Here is another table that describes standard free energy changes of some chemical reactions. If you observe this table carefully, you will notice that hydrolysis of simple esters, amides, peptides, glycosides, as well as rearrangements and elimination reactions proceed with relatively small standard free energy changes. However, hydrolysis of acid anhydrides is accompanied by relatively large changes in standard free energy. The complete oxidation of organic compounds such as glucose or palmitate to carbon dioxide and water, which in cells requires many steps, results in very large decrease in standard free energy. However, standard free energy changes that is shown in this table indicate how much free energy is available from a reaction under standard conditions. That's the definition of standard free energy change. To describe the energy released under the conditions existing in cells, an expression for the actual free energy change is essential. Standard free energy change is not sufficient. So let us consider the energetics within the cell. The criteria for reaction spontaneity is delta G, or the actual free energy change, and not the standard free energy change. Why? Consider the following interconversion: X going to Y. If the equilibrium constant K of the reaction X going to Y is less than 1, this means that the standard free energy change is greater than 0. So a couple of questions arise at this point. What would the ratio of X to Y look like at equilibrium? Where would the reaction be headed if X equals 0 molar and Y equal 1 molar? Sequestering products can drive an unfavorable reaction forward. Here, if you connect this reaction, X going to Y, to another reaction, Y going to Z, And if y going to z is favorable, then x will indeed get converted to y. So if y to z is very favorable, x to y will more readily occur. The actual delta G of a reaction in the cell depends on two things. Delta G depends on the standard free energy change as well as the reaction quotient. The standard free energy for this reaction is additive. For this reaction that is shown here, the standard free energy change for x going to y and y going to z can be added together. In addition, if you remember, delta G0, the standard free energy change, is equal to this expression. And we can insert that expression into the actual equation for the actual free energy change. The current concentrations of products and reactions is the second term that is involved. This is called as the reaction quotient, which is equal to the ratio of products to the reactants, and in this case concentration of products to the reactants. Now compare Q versus K equilibrium. If Q is greater than K, reaction will proceed to the left, which means that reaction is reverse. If Q is less than K, reaction will proceed to the right. Or this means that a lower Q will drive the reaction forward. Let us discuss the energetics of some chemical reactions. Hydrolysis reactions tend to be strongly favorable because they are spontaneous. Isomerization reactions, on the other hand, have smaller free energy changes. Isomerization between enantiomers usually happens at equilibrium. Complete oxidation of reduced compounds is strongly favorable. This is how chemotrophs obtain most of their energy. In biochemistry, the oxidation of reduced fuels with oxygen is stepwise and controlled. Most organic reactions fall within a few categories. First, cleavage and formation of carbon-carbon bonds. Cleavage and formation of polar bonds, which could be carbon, another heteroatom bond. Nucleophilic substitution mechanisms can happen, or addition-elimination mechanism can happen in the cleavage of carbon heteroatom bond. It could be CO or CN or CS bonds. Hydrolysis and condensation reactions, internal rearrangements, elimination without cleavage, group transfers such as transfer of a proton, a methyl, or a phosphate. Oxidation reactions or oxidation reductions, and this is a typical example of redox reactions wherein electron transfers happen. Let us first consider chemistry at carbon. The covalent bond between two carbon atoms can be broken in two ways. The first way is a homolytic cleavage, in which carbon-carbon bonds break into radicals, or carbon-hydrogen bonds break into carbon and hydrogen radicals. This kind of cleavage is very rare. The second way of cleavage is a heterolytic cleavage. It's pretty common, but the products are highly unstable, dictating the chemistry that occurs. In this case, a carbon-hydrogen bond can cleave into a carbanion and a proton, or a carbocation and a hydride. A carbon-carbon bond, on the other hand, can cleave into a carbanion or a carbocation, or a carbocation and a carbanion, depending on what groups that are attached to these carbon atoms. Biochemical reactions involve interactions between nucleophiles and electrophiles. Nucleophiles love nuclei. The nuclei of an atom consists of positively charged particles or protons. So nucleophiles love to react with positive charges and are electron rich. Some examples of nucleophiles involved in biochemical reactions are O-, this is negatively charged and is as in an unprotonated hydroxyl group or ionized carboxylic acid. Could be either of them. Negatively charged sulfhydryl group. Now if you remember enzymes, a serine hydroxy can be deprotonated to give a negatively charged O-. A cysteine thiol or sulfur can be deprotonated to give a sulfhydryl group. In addition to these two, there can be carbanions, uncharged amine groups, imidazole, for example in histidines, and simple hydroxide ions. Electrophiles, on the other hand, love electrons. Electrons are negatively charged, as you know. So electrophiles must be positively charged because they love electrons and are attracted towards electrons. Electrophiles, the common examples that are present in biochemical reactions are the carbonyl group. The carbon atom of a carbonyl group is electrophilic. Protonated imine group, this carbon is activated for nucleophilic attack. The phosphorus group of a phosphate is electrophilic, and a proton is electrophilic. Let us consider some common reactions that form and break carbon-carbon bonds in biological systems. The first example is aldol condensation. And in this reaction, a carbanion from one molecule attacks the carbonyl carbon of the next molecule to form an aldol product. The second reaction is Claisen ester condensation. Here, again, the carbanion attacks another electrophilic carbonyl center. And in this case, a thiol leaving group leaves. And this results in the formation of a carbon-carbon bond. For both the aldol condensation and the Claisen condensation, a carbanion serves as a nucleophile, and the carbon of a carbonyl group serves as an electrophile. The carbanion is stabilized in each case by another carbonyl. As you can see, this carbanion can resonance stabilize. It can go to this bond, and this bond can move up. In the third reaction, which is a decarboxylation of a beta-keto acid, what happens is that a carbanion is formed once this carboxyl functional group leaves. And that carbanion is again stabilized by the adjacent carbonyl group. And this is an example of a carbon-carbon breaking reaction. While substitution reactions from sp3 carbon proceeds via nucleophilic substitution mechanisms such as SN1 or SN2, substitution from the sp2 carbon proceeds via the nucleophilic addition-elimination mechanisms. Here, a nucleophile adds to the sp2 center, giving a tetrahedral intermediate. The leaving group eliminates from the tetrahedral intermediate. Leaving group may pick up a proton while leaving from the original molecule. Isomerization and elimination reactions happen in cells. And in those kinds of reactions, there is usually no change in oxidation state. For example, the conversion of glucose 6-phosphate to fructose 6-phosphate is catalyzed by this enzyme phosphohexose isomerase. And in this reaction, as you can see, the starting material glucose 6-phosphate has a carbonyl on carbon 1 and a hydroxy on carbon 2. That just got interchanged in fructose 6-phosphate now, which has a hydroxy at carbon 1 and a carbonyl at carbon 2. If you consider the mechanism of this reaction, there are two residues. One is a base and one is an acid in the active site of phosphohexose isomerase. While the base abstracts a proton and polarizes the bond, the carbonyl bond, by pushing the proton inside and carbonyl abstracting a proton from the acid. This results in the formation of an enediol intermediate. And as you can see, enediol is 2-hydroxy that is attached to a CC double bond. Now, the acid that originally donated a proton to the carbonyl now acts as a base by abstracting the proton from the adjacent hydroxy. And that pushes the bond inside and results in proton abstraction of this enediol double bond from the original base, it was B1. This results in the formation of fructose 6-phosphate. As you can see, this is kind of an isomerization elimination reaction where there is no change in oxidation state.